Hello. Okay, I was hesitating whether I should speak in Korean or English, but today I'll speak in English, and then we can do the Q&A in Korean if you want. Okay, so Chris has given us a good background on what quantum computing is, how they work. And what's really interesting is how quickly this technology is becoming more real. Okay, and when we started, Chris actually started this more than 30 years ago, when the first entangling gates in trapped ions were demonstrated. He actually did the very first work. But even when I got into this 20 years ago, it was very much a scientific exploration. But just in the last few years, I think a lot of these are starting to become pretty interestingly real. And I think what this means is the pace at which this technology is progressing. I think we're really in an interesting time when in the next possibly a few years, we may be able to find applications of quantum computing that are difficult to do otherwise. So I'd like to actually give a sense of what those opportunities may be and how some of the real-world applications are being addressed today with the prospect of when we can actually start to do some really interesting things. All right, so I will be saying some more speculative things, looking out into the future. So this is the legal disclaimer. And Chris has given background on this. I'm not going to dwell too much on this, but the qubit technology that we're using at IonQ are these individual atoms. Here, as Chris indicated, that shows 80 individual ytterbium ions. And the nice thing about them is because they're individual atoms, they're exactly identical. And the way we control them with these laser beams gives us a completely flexible control and programmability. So this one, I'll show you only half of the figure. The way we control them is, in this example, we take a single laser and split them in multiple ways. And we align each one of these laser beams to these individual atoms. And as Chris mentioned earlier, we can actually run the circuit. So let me actually just go past this, because we have already seen this just now. So what are some of the nice things about this approach? As Chris mentioned, the qubits are identical. These are individual atoms, so there is no manufacturing variation or fabrication errors. And that also the qubit states that we use have a really long coherence time, because this really is the atomic clock that we use to define the fundamental standards of what 1 second is. And basically, we have been able to add more qubits and improve the gate fidelities at the same time. Now, the gate fidelity is one of the things I wanted to mention about. Chris gives us an example of the very first digital computers that were built with vacuum tubes. Right? Now, people use vacuum tubes to build those computers in the 40s because vacuum tubes happen to have the best manufacturing technology of any electronic device in the 40s. Okay? Because the vacuum tubes were invented in the 1900s, 1905 is when Bell Labs invented vacuum tubes, and then they were used as amplifiers in telephone networks. Okay? So these were deployed at massive scales across the country in all of their telephone networks, and it was only natural that people picked that technology to build digital computers, because that was the best manufacturable technology they had access to at that point. But the problem was, these were noisy, they blew out, and they were imperfect. And what that means is, as you try to build more and more sophisticated digital circuits, this vacuum tube-based computers actually introduces errors. Okay? And that's why people started thinking about fault tolerance and all of these concepts. But when they came to the realization that these CMOS transistors represent binary logic almost ideally, perfectly, without much errors, then that whole technology took off. And that's why today we did not scale the vacuum tube technology. We actually found the CMOS technology, and then we reinvented the manufacturing capabilities to scale that. Unfortunately today, quantum computers, no matter what technology we use, when you run these gates, they have small errors. And then we have to figure out how to reduce that error to be able to run deeper and deeper and more larger and larger circuits. And that, I think, is where the other approach, advantage of this approach comes in. We have this very unique architecture where the qubits are all connected to each other. So if this actually shows, I don't know, maybe a couple dozen qubits, and if you put them in a lattice geometry with finite wires, then there are certain connections that are represented by the wires that the system can do. But for example, if you have to run a 2-qubit gate between this qubit here and that qubit here, there is no direct wire, which means that now I actually have to transfer these qubits many times before you can actually run that 2-qubit gate between those. But if you have a complete connectivity like this, as Chris indicated, in a 31-qubit system, we can do arbitrary pairwise 2-qubit gates. When you can do that, then the implementation of any algorithm onto the system becomes optimally efficient. And that actually gives you a lot of leeway, latitude into running more complicated quantum circuits. And these are all, the reason I'm saying these things is when you think about tackling real-world problems using quantum computers, all of these algorithmic advantages will make a huge difference. Okay? All right, I know Chris had planned to talk about some of the scaling technology, but when we ran out of time, I think he had to give it up. If we have a little bit of time at the end, we may invite him to come back and tell us a little bit about the scaling future. So all of these things actually makes the ion trap quantum computers very, very useful. And I'll try to indicate some of that when I give you some examples. So today is a very, very interesting times. Maybe in the last 5 or 6 years, an IonQ quantum computer, trapped ions, quantum computers available in these public clouds. And there are 2 generations of commercial quantum computers that we went to commercial services with. One is Harmony and the other is Aria. They all use this fixed beam architecture. And Harmony had 11 physical qubits and what's called an algorithmic qubit of about 9, and Aria has 25. And then the latest system that we have built is called Forte. And this one actually has a higher performance than the other. And here we use what's called a deflector technology, where this individual addressing beam, instead of being a fixed array of beams hitting the ions, we can actually steer these beams, and there's just more flexibility into this. But today we're in an interesting time. I mean, IonQ already has 3 different generations of quantum computers of higher and higher quality in the clouds. But there are many, many, many other quantum computers that are available to you through a cloud services or by working with various vendors directly. We have access to, for example, IBM has many generations of superconducting-based superconducting qubit-based quantum computers that are available. Rigetti has similar ones. Many companies are now starting to come up with neutral atom-based quantum computers. So if you actually have an idea that you want to tackle a real-world problem with quantum computers, you have access. You have a lot of options to access these quantum computers online. Okay? And you can actually approach these companies or university labs to actually run this. For example, the SKKU Center here provides access to both IBM and IonQ systems, and I think it also allows access to D-Wave systems. So we're in a very interesting place where even if you don't know how to build a quantum computer, if you have a good idea, if you have a good way to tackle your problem with quantum technology, you have an opportunity to actually go do that. Okay? Now, that's great. But at the same time, we're kind of going back into the 1970s, where people have come up with digital computers, but we have very limited number of people who know how to use digital computers to their advantage. And we only have very small number of applications where people have thought about using digital computers to tackle their problem. Today, there is no problem that we don't tackle with digital computers. Pretty much every problem, because you use your cell phones and your internet and your computers to do everything, right? Even like writing papers, word processing, all of those things are done using digital computers. So I think one of the interesting opportunities, we're still in the very early stage where new ideas to tackle a real world problem using quantum technology is your bottleneck. We don't have a lot of people who have thought about new ways to tackle problems with quantum computers. And that, I think, is an opportunity. It's an opportunity for everybody in this room to really think about new ways to tackle your problems using this new quantum technology. So in order to do that, so and as I mentioned, there are all these quantum computers that are available out there. The question is there a good benchmark that actually tells you how powerful these quantum computers are for the types of problems that you're trying to tackle? So I'd like to see if I can indicate that. And this benchmarking is basically measuring the performance of quantum computers in a meaningful way. Okay? So the key is you got to measure what matters, and then you can actually make real progress. So what is the right metric to track progress in quantum computers? And you think about these quantum computers, and company A has 10 qubits, but company B has 100 qubits, and company C has 400 qubits, and some companies have 1,000 qubits in their roadmap, and so on. We hear a lot about all of these things, but how important is having a lot of qubits? Now they are a metric, but does that actually tell you what you can run? What kind of algorithms you can run with that computer? And it turns out that the counting number of physical qubits in your system is actually not very helpful. For example, when you're trying to buy a car, it is similar to counting how many bolts you have in your car. Okay? It is a metric, but it actually does not convey the utility or the usefulness of that car. So when you buy a car, from a user's point of view, you think about things like this. How many people can I fit in the car? What is the gas mileage I get? How far can I drive? How safe is it? If I'm thinking about having my kids in the car, do I feel comfortable putting my kids in the car, and so on? So a lot of these our usefulness is measured from the user's point of view rather than what actually component counts that matters. And even gate fidelity, when you think about, I said every quantum gate actually now have finite error. And that actually prohibits you from making infinitely deep circuits, because once you concatenate more and more gates, the errors will compound, and eventually the performance goes down, right? So we have to fix that. So these are all device-level metrics. And when you think about the digital computers that you bought, I'm sure there was a time when you asked, how many transistors do I have in my chip? But we don't ask that question today. When you buy your cell phones, you don't ask how many transistors you have in your chip. But we often think about the storage space, right? How many gigabytes of memory do I have? Because that actually relates to the applicability of different types of applications and how much data you can store, and so on. So sometimes these device metrics are useful, sometimes they're not. But these don't necessarily translate to what a user can do with this computer, with this quantum computer. So this problem is also prevalent in classical computers as well. And in classical computers, what they have done is they came up with a benchmark that is more based on use cases and algorithms. Okay? So this SPEC benchmark, which was established in 1988, and it's been in use for about 35 years, and is still today very valuable. What they do is the SPEC benchmark, there is a standards body or group of people, and they come up with representative use cases for a digital computer. And there are usually several dozen of these examples. And then they actually have a measure, a test that I can do against each of these use cases. And then they actually run tests, and all the vendors run the tests against these SPEC benchmark algorithms. And the user can actually now go and say, I'm interested in an application or use case that looks very much like the second algorithm. And then they can actually compare performance across different devices. So this is actually a much more useful way for the vendors who build machines to communicate with users who are actually using those systems. So in order to actually measure progress, it's very helpful to think about real-world problems, representative real-world problems that quantum computers can solve, and then figuring out how to actually create benchmarks and metrics around that. And that is actually exactly what was done by a standards committee at QEDC. QEDC is the Quantum Economic Development Consortium. It is a US industry consortium. And they created a small task force to think about what is the best way, what are different ideas that you can use to benchmark quantum computing performance. So about maybe 3 years ago, the group came together and said, okay, why don't we actually try, just like spec benchmarks, why don't we come up with a bunch of different algorithms and use cases, and then see how well quantum computers can run that. Okay. Long story short, they actually made a plan of, for example, quantum Fourier transform is a very characteristic quantum algorithm that are actually used in, say, Shor algorithm. Okay, Shor algorithm is eventually done by quantum Fourier transform. So what they do is, okay, how well can your quantum computer run a quantum Fourier transform? Turns out that you can build a 2-qubit quantum Fourier transform, 3-qubit quantum Fourier transform, 4-qubit, 5-qubit, and so on, all the way to 20, 30, 50, 100-qubit quantum Fourier transform. So let's actually see how big of a quantum Fourier transform your quantum computer can run. And here there is the width, which means the size of the circuit, how many qubits are used in the system. And then there's a circuit depth, which represents how many gates are involved in running that quantum Fourier transform. So each problem actually maps to a point in this circuit width versus circuit depth graph. And then when you run that algorithm, the color plot tells you how successful you're going to get to the right answer. Meaning when you are in the blue or green, that means you have a high probability of getting the right answer. But when you're in the red, that means you're not getting the right answer because your error dominates, and then you get junk, you get noise. Okay? So the question is how far up in this algorithm size you can go and still keep your results to be in the blue is like the key name of the game. That means you can run more and more complicated quantum circuits, and that just means that generally the quantum computer becomes more powerful, and you have a good sense of what the algorithm that you're interested in can execute against this quantum computer. So we actually said, okay, that's a great idea. And now let's think about if we can actually extract a measure out of this. And that's what's called an algorithmic qubits. And it's very different from how many qubits you have in your system. This actually means how many qubits can you actually utilize in your real algorithm execution. Okay? So this actually, I think this is something that Chris and I thought about for a while. And when you say an AQ of n, that means I can actually use n qubits in my system and run circuits that involve about n squared entangling gate operations. Okay, so this is a number that represents how many qubits you can deploy and to run an n squared entangling gate operations. So it actually measures both the qubits that you can deploy, but also the number of gates you can run. Okay? And it's what's called a volumetric benchmark. Volumetric benchmark means it's not counting just the qubits, but it's also looking at how deep of a circuit you can run. And if you actually take this definition, by the time you get to about AQ of 60, that means you have 60 qubits, and you can run about 4,000 entangling gate operations, or 3,000 to 4,000 entangling gate operations. Now that quantum system becomes extremely difficult to simulate. Okay, in the most generic case, if you actually can run that many qubits with that many gates, entangling gate operations, you can get into a regime where the simulation of this system becomes impossible classically. Okay, so again, you can have a quantum computer with 1,000 qubits, but if you can only run very shallow circuits, like in Chris's last graph, if you can only run shallow circuits, then it is totally simulatable. You actually have to have large enough qubits, but also deep enough circuits you should be able to run to really get to the quantum advantage. Okay? All right. So this is kind of where ARIA is. Now we actually measure these. So here, again, is a plot of how many qubits you can use in the vertical axis, and then how many entangling gate operations you can do in the horizontal axis. So when you say AQ of 25, it's a box that is 25 qubits tall, and then 25 square, which is 625 entangling gates deep. Okay, so we can actually plot this gray area. And what you want to do is, based on these 6 algorithms that were identified in the QEDC's paper, we want to make sure that every circuit within this box actually succeeds with some probability. And that's how we define. Now, if your circuit starts to fail at very large qubit count or very deep circuits, then you have to shrink the size of your gray box until everything within that gray box passes.
Then that smallest size gray box you can draw is your algorithmic qubits, which means that everything in here passes. So with ARIA, we have an AQ of 25, which means I can run up to 25 qubit Hamiltonian simulations, phase estimation, quantum Fourier transform, and all these other circuits, up to about 625 entangling gates. Now, our latest is IonQ Forte, which actually has 29 algorithmic qubits, which means that you can see that it can actually run much bigger and deeper circuits now. Okay, so now, of course, when you use these things, the fact that we have high gate fidelities and also the fact that all the qubits are connected to each other is a huge advantage. Because when you try to, say, take a Hamiltonian simulation or phase estimation and try to map it onto an architecture where they're very sparsely connected, then each gate operation has to translate into many, many gate operations, and then the success probability can go down very quickly. So in order to actually get this high performance, the architecture matters. And here I also want to remind you that we have very advanced compilers, and these error mitigation techniques are extremely important to get to the right answer. Okay, so when you're computing AQ, you are allowed to use these two techniques and then you're allowed to innovate on these techniques to make sure that your quantum computer gives you the right answer. Okay, so some of these high AQ, it is very clear. The data shows that trapped ion systems tend to have a much higher AQ than the solid-state counterparts for various reasons. And I think if you look at the QEDC paper, they actually have some real data that compares how well ion-trapped quantum computers do compared to the superconducting and other solid-state systems. Now, I'm sure future innovation can make that work better. But once you have a relatively high AQ system where you can run really interesting and arbitrary structured algorithms, then you can actually start to run real-world applications. And I think this is a really exciting area in my mind because the applications now, the QEDC algorithm here, these are, in some sense, these are very canonical examples. They're like textbook examples of what quantum algorithms are. But I think with that kind of a performance, we can actually start to tackle really interesting real-world problems. Okay. Now today, some of these applications of real-world problems we can tackle is still relatively small because the quantum computers are still in its early stages and the capacity is limited. But what's really interesting is we can actually continue to come up with new ways to tackle the problems using completely novel quantum approaches. So I'm going to give you some examples of these. We actually have been working with many, many different collaborators, either in academia or in other companies, to look at these problems. And in many cases, we actually walk in and start the collaboration, and the user brings us problems that we never thought there was a quantum approach to it. Okay, we just and these are problems that are brought to us without people recognizing there will be a quantum solution. And then what happens is we sit down and see if there are new approaches we can invent and develop using quantum to see if we can actually do better. And in many cases, we find some really interesting insights. And sometimes, initially when I thought that somebody brings a random problem and we try to come up with a quantum way of solving it, I would have thought that the probability of us finding something interesting was relatively small. But the answer is no. I think in most cases, we find some really interesting insights. And then we can actually build upon those things and go and tackle more and more exciting and potentially more challenging problems. So some of the application focus areas that we have been looking at is quantum machine learning. Machine learning is a very large field, and therefore quantum machine learning is also a very large field. So here I'm going to give you some examples of the machine learning work that we have been doing in the past. Optimization is another very practical area, and quantum optimizations have been explored for some time. We also continue to look at chemistry and material simulation problems. And very recently, we've been looking at some interesting aspects of natural language processing. And Dominic here is one of the world's experts in natural language processing, but also when it comes to quantum natural language processing. He's probably one of the world's most experienced person. So feel free to approach him and ask about all the fun things he has been able to do. So these are just some examples of collaborative work we have done with various partners, and that's already been published. But we're also, we have a lot of other work that are in the pipeline, which I am hoping we will be able to share with all of you in the near future. So first is with GE and Fidelity's Center for Advanced Technologies. We have been looking at financial risk management. Again, some early ideas on how to use quantum generative adversarial network, quantum GANs, to actually create some samples and models. We've also found out that quantum models are extremely effective at looking at data that has a lot of internal correlations. So I'm going to give you some example of these. With Airbus, we've been looking at some logistics problems like cargo loading. With Hyundai, I think some of our collaborators here, we've looked at some battery chemistry, and we're starting to look at some catalyst reactions and creating some new approaches to understanding that. We've also been doing quite a bit of object detection in images. This is, again, machine learning problems, image classification. And then with Zapata, we have been doing some GAN-type image processing. And more recently, we've actually started looking at some of the predictive maintenance. And this is where if you have a fleet of, say, airplanes or rental cars, or machines, and you would go through regular maintenance, and you collect your maintenance data. And by analyzing the maintenance data, you can often predict when something will fail. Because we actually have a lot of data that shows if this pattern of maintenance data is collected, then something happens, right? So we can actually start to predict what that may be, and then we can actually go and try to kind of fix them in advance so that the fleet operates more efficiently. So that's the kind of application. It's actually quite widely used in airplane maintenance, but we're finding out that some new methods in quantum seems to be doing a little bit better. So Willie, who is here, back there. So Willie has been doing this kind of work along with some of the other machine learning. And then chemistry is our expert is Luning, who is here. So Luning will be is a real expert in coming up with more efficient ways to simulate chemistry using quantum. So these are the three instructors that we'll have throughout the week to give you some real examples of these quantum computing applications. So let me give you some examples. And still, as I said, quantum computers today don't feature quantum advantage. Meaning, even at AQ29, you can simulate what's going on using a classical computer. But by the time you get to AQ about 60 or so, you will not be able to do that. So the question is, what are some of the opportunities that these new approaches that we're inventing to tackle real-world problems in quantum provides? And can we actually push its advantage at around AQ of 60 to 100, which we should be able to build a machine like that in the next few years? So the first is image and object recognition. And here, the image recognition is a classic example of that is convolutional networks. And these are the examples that you're given. Somebody gives you a whole bunch of cat pictures and a whole bunch of dog pictures. And your goal is to see if you can create a mathematical model that can identify dogs and cats and separate them. Okay, and that's how our brains learn how to do that. When babies are born, they have never seen a dog, they've never seen a cat. But as they grow up, mom and dad points out, that's a cat, that's a dog, right? And over time, they create some mental model of how to differentiate a dog from a cat. And then when later in life, when they see a dog, they know it's a dog. They see a cat, they know it's a cat, okay? And this is actually a classic example of solving this is this convolutional neural networks. But there are other ways. These are called so-called image classification problems, where you actually have to process the characteristic features on your image very carefully, and then you create some separation between them so you can classify A from B. And one of the examples that we have done in the early days, and this is work we have done with QCware maybe 3 or 4 years ago, is we think about what's called a near-centroid classifier. So in this case, we use a MNIST database of either images of irises. These are 3 different types of irises. and there is a standard database for that. Or we look at handwritten digits. These are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 different classes of handwritten digits. And the question is, can you actually separate them using a quantum algorithm? Okay? So although these are not like really hard problems, these are real-world problems that you're starting to tackle here. So what we do is we create first of all, we have to analyze these images to capture the characteristics in this image. And then we actually create some kind of a distance metric and measure, for example, different clusters. And then we can actually create a centroid, calculate what the centroid of all of those labeled data is. And then when you're given a new data, then you measure the distance from that new data point to these 3 centroids. And then whichever is the closest centroid is how you identify your image. Okay? So that's how you do it. And this is an example of handwritten digits. So there are 3 data points here. The black diamonds are a near-centroid accuracy for classical near-centroid algorithm. Okay, so that black diamond is kind of the reference you want to beat. Blue is our quantum algorithm. And then orange is a quantum algorithm with some error mitigation techniques. Okay, and you can see that when you're trying to compare or identify 0 and 1, they look very different. So it's relatively straightforward to identify these two. And you can see that with an 8-qubit model, your quantum computers, after error mitigation, does a perfect job. It doesn't create any errors. 2 and 7 is a little bit harder. You can see that they look kind of similar. Right? So there's about 10% error both in classical and also in quantum. We've also looked at identifying or classifying 4 different types. And eventually, we also tried to classify 10 different objects. And you can see that the quantum algorithm performs very similar to classical algorithms. Okay, so this is the first example of real-world image classification with a very small quantum circuit, like an 8-qubit quantum circuit. Oops. Okay, now, if you can discriminate different characters, then you can actually create images too. And this is the adversarial network. And the way it works is like this. When you are trying to, if you have a discriminator that can tell a real image from a fake image, what you do is an adversarial network is you start from a random noise, and then you create some kind of an image, generate a fake image, and then you ask this discriminator, see if it can tell this fake image from a real image. Okay? If it can, then that means your fake image is not looking good enough. And then you go back and improve the generator to generate an improved image. And you keep doing this until the discriminator cannot distinguish. And then now you have created a fake image or data that looks very similar to the real world. Now, have you seen the movie WALL-E? This is one of the Pixar movies in WALL-E. And if you look at that movie, and this is a little robot that's left on the Earth and trying to clean up all the mess. And the Earth is described as this, trash with all kinds of trash. And if you look at the background, there's a lot of like noisy data with trash that's in the background. They didn't go and draw those one by one. They actually used a generative adversarial network to create those background images. Okay, so this is sometimes very useful. So here, if you look at these characters on the right, and these are 0, 4, 7, 5, 4, 5, 1, 3, 6, 3, 6. Now these images were actually generated by an IonQ quantum computer, okay, using this method. Okay, so here is an example of a quantum generative adversarial network. Now, of course, these are very, very simple images that we're generating, only 10 different types. And this work was done probably about 3 years ago as well. But with very early quantum computers, we can actually start to generate some real interesting images, right? So the question is, now, when you look at an image generation like this, maybe all you're doing is like doing fake image generation. But this generative adversarial networks are very, very interesting and important. For example, we all know about ChatGPT. That's a language model. That's a generator. You train this thing, and they try to generate sentences that are so close to the real world that people won't be able to tell the difference. So that's like a really advanced generative models. But we've also seen recent examples when people are trying to do drug discovery. And what they have is they have a whole bunch of molecules that they can synthesize, but testing each molecule is extremely expensive. Okay? But there are a finite number of molecules that have been tested where some real-world data exists, but we don't have a lot of data. We have very limited data. So the question is, can you then run a generative model that correlates from this big database to the data that was actually measured and start to predict some of the combination of molecules that people should be testing? Can you actually select some highly promising candidates to explore? That type of problem actually has some real economic value, but I think people are starting to look at these kinds of problems now. And really the question is, can you do this more efficiently with a quantum model than classical model? I think those are some of the really interesting areas where real-world impact for quantum computing can be found. Okay, so this is another problem. Again, we work with this from Hyundai Motor Company's Institute for Advanced Technology Development. And they gave us this problem maybe 2 years ago as what we call a toy problem. They gave us a picture of a whole bunch of German road signs and asked us, can you actually use a quantum algorithms to actually classify these German road signs? And these are now, compared to these, which is only a very small pixel data, these are much more complicated images now. Right? So we're trying to see if we can tackle this. And the way we do that is first we actually use a classical technique to really compress the image. And here we actually used a classical neural network called autoencoder to actually compress the image to a relatively small, what we call the latent space vector. But we also improved some of these very standard autoencoders to make sure that we can compress this image into something relatively small, but then fully recover the images. So this is the original image on the top, and then it was heavily compressed and then reconstructed. And the fact that these images at the bottom look very similar to the images on the top means that when the image was fully compressed, it actually still captured the essential property of that image. Okay? Because if by compression you throw some information away, if you threw critical information away, you will not be able to recover fully. But here in this autoencoder, we were able to do that reasonably well. So now what we have is we have this in the latent space, in this highly compressed space. We have a very short vector, and we would actually take that short vector and then put them into a quantum state. We load it into quantum state. And then what we did was we created this model. And this is a trainable model. And in this case, we have, and this is a fully quantum circuit. And you can see that there are U1, U2, U3, U4. There are 4 different quantum circuits that we supply. Each U has actually 15 independent parameters. And then we actually apply this U1 to all the nearest neighbor qubits, U2 to every other qubit, U3 to every 4th, and U4 to every 8th. And we can actually now, using this model, we can create a 4-qubit model, 8-qubit model, and 16-qubit model by which we try to learn the properties of these real road signs. And then we can actually see if we can do some classification on that. Okay? So this is a real quantum circuit. And I think the result is we were doing reasonably well. So here, for example, this on the left is a 4-qubit model. That's an 8-qubit model, and that's a 16-qubit model. And in the 4-qubit model, when you're trying to do a 2-class classification, meaning if you're just trying to tell between A and B, we were able to do pretty well. Just first look at these orange bars. These are the quantum classifiers accuracy done by an ideal simulator. Okay? In 4 qubits, you can actually do a perfect simulation of quantum states. And you can actually see that it tells 90%. 2 classification, you can do it with 90% accuracy. By the time you get to 6, 8, and 10 different classes, the model was just way too simple to actually be able to discriminate too many. So the accuracy drops very quickly. But by the time you get to 16 qubits, the accuracy remains pretty high. 10 category classification can succeed with 60% success probability or accuracy with a full quantum models. Okay, so what this means is as your quantum model gets more sophisticated, the accuracy goes up. And then this gray is actually a real data taken from a real hardware. meaning so orange is an ideal computation and gray is a real quantum computer output. And you can see that the accuracy drops in a real quantum computer because the real quantum computer actually have some errors, but still they're doing a reasonably good job. So now the question is, why is this interesting, right? Why is this quantum model interesting compared to classical models? And what we have seen is in many cases, quantum models can capture the complex structure in the data more efficiently than classical models. Meaning classical models may need a lot of parameters in the model to capture the properties, but quantum models generally require much fewer parameters, and it also generally takes much less data to train. Okay? And that's because by using building the models in this quantum mechanical Hilbert space that is much bigger, we can actually create much more complex models in a much more efficient way. So it is, I think people are starting to appreciate that these quantum models are more expressive, meaning you can actually use fewer parameters to actually capture more complicated structure in the data. And that can be very useful, especially in applications where you don't have a lot of data to train a very complicated model. All right, so I'm going to give you one more example of machine learning. And here, we actually are looking at what's called the joint probability distribution using a method called copyless. And here in this orange, what we have is we started from a real-world stock market data. Okay, so this is a collaboration we had with Fidelity Center for Applied Technology. And here they first brought us Apple and Microsoft stock prices, historic stock prices for about 8 years. And our goal was to see if we can capture some underlying correlation between Apple and Microsoft stock. And because they are both in tech sector, they actually move together in most days, but they are also competition. For example, Apple has an iOS and Microsoft has Windows, and they're competing products. So in most cases, they move together, but sometimes if one of the products do well, then it actually is bad news for their competition. So sometimes they move against each other. And when you look at the relative correlation between them, you can see that they are largely clustered in the middle in terms of data, but there's also a lot of outliers and scatters. And that's what the real data looks like. And the question is, can I create a machine learning model where the probability distribution looks very much like the real data? Because if I have a probability distribution that mimics real data, I can actually sample from that and do a lot of predictive studies. Okay, so that there's some real value in doing that. So you can actually use classical GAN to try and create this data, this distribution. And you can see that it actually produces the middle stuff really well, but you can see that there's some pretty clear boundaries here below which you have no data points. And these outliers are not very representative. They're not predicting the outliers as well. And this is after 20,000 iterations of training. Okay, so this is very expensive training. But if you look at quantum GAN or quantum circuit board machine, these are different types of quantum machine learning models. You can see that we can actually reproduce these outliers much better. And also the number of training iterations drops dramatically. Okay? When the number of variables increase, here we're looking at only two correlations between two different variables. But once they go into the generically correlated, like 10 to 15 parameter model, it becomes extremely expensive to train a classical model to this. So the question is, why does it work, right? Why does this work so much better in quantum? And one of the insights we have is when we use these quantum circuit board machines, we actually first create a quantum model where there is an underlying entanglement. Okay, we use entanglement to create quantum models where the variables are fundamentally correlated. And that's something that's really hard to do in classical models. And because of this underlying entanglement, we are much more effective at capturing the correlations. And that's our current insight. So when it comes to data that is highly correlated, I think quantum modeling can actually be extremely effective. So here in this work we have done with GE's financial research arm, we've extended this work to 3 and 4 variables. Again, these are some KL divergence metrics that we're using as after we evaluate a lot. You can see that in 3 variables where our quantum computers actually experimentally we're doing very similar to simulation. But by the time we go to 4, there's some discrepancy, which means that we need to continue to improve our quantum computers. All right, so in the interest of time, I think we need to wrap up. I'm going to just do one more example of this optimization problem. And this is a work we have been doing with Airbus. And there is this cargo loading problem. If you have a whole bunch of cargoes of different sizes that has to fit into an airplane with a lot of constraints. And the constraints, I think, so this is the model. We have 3 different types of cargoes. And there are kind of segments in here that you have to fit in. One is a type of cargo that fits one segment. 2, you need 2 of these boxes to fill a segment. And 3, you need 2 segments to fill it. So we have 3 different sizes of cargoes with different weights. And the goal is to make sure that you stack this up. And then there are some constraints, meaning you cannot overload the plane, meaning the total weight that goes onto a plane has to be under some limit. But you also want to make sure that you don't put too much weight on the front or the back so that the airplane doesn't tip. So there are lots and lots of constraints like that we put in. And then we actually ran what's called a QAOA algorithm, quantum approximate optimization algorithm. And we ran this on our latest machines with about up to 28 qubits. So we can actually run these fairly complicated optimization circuits that have been extremely difficult to run in most other systems. And then, I think there is a little bit of chemistry, but let me actually see if I can, in the interest of time. You can also ask Luning, or we have a couple of Hyundai team members here who have worked on this together. So what I'd like to do is maybe summarize where we are. So these quantum computers were very much researched. Can you do qubits? Can you do gates? And so on. But we're coming to a point where these quantum computers are actually available to you to use. And if you actually have a real-world problem, and if you think hard enough, we actually have been able to come up with new approaches that takes advantage of these quantum nature of your models or your computational techniques to actually create solutions that can tackle real-world problems. It's a very, very exciting time to be. And the question is, what is the impact? Can we actually start to win in some of these examples? So in IonQ's roadmap, we have we focus on algorithmic qubits as our metric because we believe it actually tells users the types of algorithms and problem sizes they can tackle. So we have a goal of achieving AQ 25 and 29 in the last year and this year. Next year is 35, and then in 25, we're targeting to develop a machine that can achieve AQ of 64. And as I said, if you can get your AQ to be about 50 to 60, then this will be really difficult to simulate classically. Now, that does not necessarily mean that there are useful things we can do with it, and that's where the opportunity for innovation really lies. And I think we believe that machine learning algorithms can probably start to provide some interesting advantages by the time you get into the 2025 timeframe with AQ of more than 50. And then material simulations and some optimizations, we may need even larger machines. Again, this was our projection from before, is real complex chemistry simulations may have to wait. But the machine learning, when you look at pattern recognition and pattern prediction, machine learning has a lot of applications in all kinds of places. We talked about predictive maintenance. We talked about some drug discovery applications. There are some pattern recognition that can tell you that has implications in security applications. And earlier today, we were talking about weather prediction. Now, weather prediction, if you want to do the full computational fluid dynamics, that may be a difficult problem to solve with quantum computers in the near term. But if you look at certain kind of observation data to prediction of what kind of weather phenomenon that you observe, that is actually a pattern recognition problem looking at very rare events. So this machine learning can actually have a very, very broad applicability to many different types of applications. And I think when we go to a regime where we don't have enough data, right, that's where quantum computers come in. Remember, quantum models tend to be able to train with fewer data and fewer iterations and actually get you pretty accurate predictions. So I think there are many open opportunities, very exciting opportunities, where in the next few years, we may be able to get to applications and use cases that actually feature and demonstrate quantum advantage. These are some of the application areas. I'm not going to go into the details, but again, machine learning classification, image classifications, chemistry simulations. These are all we have developed many interesting quantum approaches that tie into some industry example use cases. So the real open questions is everybody in this room can think about new applications that are relevant to their industry. Okay, so some of the real, these are all very speculative, but traffic prediction, aircraft loading, some of these we're doing, route optimization, fraud detection by looking at some unusual patterns in the data, production planning for optimization, price and demand, supply chain management, sets and placement, smart robotics, all of these areas, I think there are ideas that we can come up with where quantum machine learning as an applications can actually make an impact. I think we're at this point we're quite excited about some aspects of quantum machine learning where even in the near term we may be, because the quantum models are highly expressive and they can actually tackle real world problems. We believe that some solution development in quantum computers may be able to hit some really interesting applications in the next few years. And in order to do that, we need some technology-relevant problems that all of you in your industry can bring to the table. And then we need a lot of domain experts who are trained in quantum computing and can think about quantum algorithms. And that's an area where I think a lot of our internal experts can actually work with you to actually develop some more insights into this. And then we really need to create a vertically integrated quantum solution, and we could do that with a lot of collaboration and partnership. So with that, I'd like to thank you for your attention, and maybe Chris and I can come up and answer any questions you might have from the last couple of hours lectures.